Good morning. It is with great joy that I get to introduce the inimitable Joe Michael this morning. Dr. Joe Michael is a senior scientist at Sandia National Laboratories in Albuquerque, New Mexico, where he works in the Material, Physical, and Chemical Sciences Center. He received his bachelor's, master's, and PhD in material science and engineering from Lehigh University in Bethlehem, PA. Prior to his employment at Sandia, Joe was employed as a senior research engineer at Bethlehem Steel's Homer Research Laboratories. Joe's current research focuses on the use of electron and ion beams for the characterization of materials utilizing high-resolution imaging, elemental microanalysis, and crystallography. Joe has published over 200 papers in this area and is a co-author of the leading textbook on scanning electron microscopy, which most of you in this room probably know. Joe's also won a crap ton of awards, but I'm not going to read them. And with that, I give you Joe.
Well, thank you for that nice introduction, Susie. It's the first time I've heard the word crap ton in a seminar before, but that's fine. I feel sort of responsible for Susie being here. She came to my course at Lehigh and met Emma, and that was the start of her coming here. And so I don't know if I need to apologize or wait for So anyway, man, this is loud. Is that okay? Hang on. There we go. So anyway, I'm going to tell you a little about electron backscatter diffraction. I've been working in this field for a few years, probably more than 20. And I think it's a great technique, and I think the one thing I'll say is if you're buying a new SEM or if you're an area or a group that likes to work with crystalline materials and you don't have EBSD, you're losing ground. So I'll leave it at that. Just wanted to say that this technique is not all that old. I wrote my first papers back in '92. And what this is a plot, a number of publications versus a year. I just did a Google Scholar using some of the terms we use for EBSD through the years. And so the red curve is all publications that just use those terms. And so you can see it's quite a lot now, over 3,000 publications just in 2017 alone. I added the word mineral to my search because that was the best thing I could think of for geology was mineral. And you notice that the geology community is really starting to take off as well with this sort of a technique. So there's a lot of papers out there, a lot of applications for EBSD in both planetary sciences and geology, mineralogy, and of course in metallurgy and general material science. So it's a technique that's really starting to move on. Just some microstructures that I found really attractive. This is basically a nickel iron aluminum alloy. This is taken with 80 nanometer steps, so the resolution of that image is about 80 nanometers. This is a representation of the orientation of those phases within that microstructure. And down here, we've identified the phases by their crystallography. So you have the red is the body center cubic ordered nickel aluminum. The blue is the face center cubic nickel 3 aluminum. And the yellow is a martensitic phase. So we can do phase discrimination with this technique as well. The nice thing about this is I think, really makes the SEM a complete tool now. So with an SEM, when it first started, we took beautiful images of surfaces and saw fracture surfaces and all sorts of neat things. As we added EDS or chemical analysis, WDS, we now made a tool that could do both morphologies and then elemental analysis. And now with EBSD, we've really covered the gamut. We have imaging, we have analysis, chemical, elemental, and now we have the crystallography of the sample as well. So it makes the SEM a complete tool for materials characterization. And in some cases, I think it pushes the TEM to sort of the background for what we want to do. EBSD right now, it's great for orientation mapping as shown here. So this map represents the orientation of those various phases using a color key, and I'll talk about that in a bit. We can talk about grain size and grain boundary analysis if you're interested. And by grain boundary analysis, or I'm talking about also orientation relationships between phases. So we can study those quite nicely. We can do texture, of course, if you're interested in the texture of a rolled steel or a rolled material or something plastically deformed, we can deal with that. We can do this phase identification, as you see here. Given a list of phases, we can pick out the ones that match. And then finally, this last one down here, which I won't talk about much today, is the newest thing, is strain analysis, where they're starting to measure from point to point the elastic strain and some of the plastic strains within a sample. So it's a technique that's got a lot of different applications. And I think it does really has become one of the premier tools for microstructure analysis. So the other thing is you can go over a huge range of length scales. So this is the common Gibeon meteorite. You can go out and buy this if you want on the numerous websites. So this scale bar here is 5 millimeters, and this is an orientation map of Gibeon. And we'll talk about that a little later in the talk. So this spans quite a huge area. And this, I think, was done at 4-micron pixel spacing. So we can go in here and look at smaller areas in detail if we'd like. We can also do a new technique called transmission Kikuchi diffraction, where we make a thin sample using a fib or any of the other techniques used for TEM. And you can see here, this is taken at 5 nanometer step size. So this little area here was one of these little areas. It's almost too smart a mark on this guy. And you can see all these nice little austenite, sorry, that would be taenite, I guess, to you geologists, right? It's the FCC phase inside the camosite matrix, which is the BCC or ferrite to us metallurgists. I was telling Susie earlier, I tried to look up who came up with the idea of ferrite or camosite first. And unfortunately, I think the geologists beat us by quite a few years. So I guess we made up the name ferrite, and you guys had the original name camosite. So anyway, we span this huge range of length scales now with the technique, all done with the same tools, the same microscopes. And so really quite a nice, and I can't think of another technique that really can do this sort of breadth, down to the nanometer, all the way up to the millimeter scale or bigger. What else can we do with EBSD? So we don't have to have a flat polished surface. In the literature, you'll find that tin whiskering is a huge deal with microelectronics these days because we took lead out of solders and then we grow these tin whiskers that can get quite long and cause shorts. There's lots of data in the literature about tin whiskers causing problems in cell phones, cars, and satellites. So it's a big problem. So one of the questions is, how do these things grow? Can we determine that? And yes, of course we can. There's a plot. This is an inverse pole figure. And these are the various growth directions for about 100 whiskers that we characterized using EBSD. So we can go through and we can actually figure out which ones have the 001 growth direction, because tin's tetragonal, so it's not the same as the 010. And you go through that and so forth. So quite powerful. The other thing we can do is we can start looking at things in 3D. So if you have a fib and you have an EBSD on there, you can do this slice, an image, slice, an image, slice, an image. And so this is basically 200 slices through one of those tin whiskers, about a 200 nanometer cube pixel. And if Microsoft helps me, we can actually then take that and rotate it around. You can take a good look at the structure and how that whisker has grown out of the substrate tin. So this gives you an idea of, you can see the grain at the base of the whisker, that blue guy. It grows a whisker of a somewhat different orientation out of it, and we get more detailed knowledge of what's going on in the structure. So lots of different things that we can do with EBSD. So I think it's a really powerful technique. So how does this thing work? So let's start with the patterns. So here's a typical EBSD pattern. I went back to my archives and found some geological examples. This is wolfenite, purchased at the local mineral store in Albuquerque. So I guess it's wolfenite. It was labeled that way, and it looks like it. So it's a lead moly oxide. The patterns you see here, this was achieved at, I think this was 38 kV in an SEM, one of my older SEMs. But the patterns are quite beautiful, in fact. I find them very fascinating to look at. One can look at that and really start to understand the crystal structure if you know what you're looking at. So what we have here are these parallel lines. Those are the Kikuchi bands. The spacing between those is twice the Bragg angle, right? So we can measure something about the despacing, although you'll notice the edges of the bands are not quite sharp, and so it's not very accurate. The other thing you notice is all these intersection points between the various bands. Those are the zone axes. And of course, the angle between the zone axes tells us an awful lot about the crystal structure that we're looking at. So if we can measure the angles between these planes and the angles between the zone axes, we can tell you what the crystal structure is. And we can tell you what it matches to. And in fact, we can tell you the orientation of the grain that it came from very accurately. Typical accuracies are sub-degree with this technique, so maybe half a degree or less in orientation accuracy. Go back one. What's the scale? Angular scale? Well, I don't think it means anything in diffraction space, right? So this is really a diffraction pattern, right? So the angle here, this is more than 90 degrees corner to corner. So it's to think of it as a picture of reciprocal space. And so that's a large angle. And that's the other nice thing, and thank you for bringing that up because I forgot to say, you know, when you look at TEM, you look at an angular space that's maybe 6 degrees, maybe 7 degrees on a new TEM. Here we're seeing nearly 90 degrees of diffraction space in one shot. So it's really nice for actually doing crystal structures. There's other features in here that we can use. I don't know if you see these parabolic or circular features. Those are actually the intersection of the Ewald sphere with high order Laue zones. And that also gives us a spacing coming out of the page in the crystal structure. So we can do some other sort of reduced cell calculations. Anybody does X-ray here, you can do reduced cell calculations to actually identify the phase from one pattern, or at least identify the crystal structure. So how does this actually work? We take our electron beam. In a normal SEM, if we illuminate an amorphous sample with electron beam, we get this distribution of backscattered electrons. If we then do that with a crystalline sample, you can actually see that there's perturbations on here. And this is schematic, but people have actually done this experiment. Those perturbations are due to Bragg diffraction in those directions. Okay, so we're seeing now the influence of Bragg diffraction on our backscattered electrons. And that's really the basis for this technique. If we look at what really happens in the microscope, so here's our incident electron beam, we actually tilt the sample over to some high angle. It really doesn't matter what angle that is as long as it's more than like 50 degrees or so. That does bring some operational difficulties because now when you move the sample around, it doesn't move in the plane you're used to seeing it move in, but we can work around that with modern computerized stages. So our electron beam comes in, impacts our sample. We have diffracting planes in the sample. We get diffraction from those planes. Those diffracted beams come out in a very flat cone. The apex angle of the cone is 90 degrees minus the Bragg angle, so Bragg angle is maybe a degree for 20 keV electrons. And so it's a very flat cone. We intercept that with a phosphor screen, and so it looks like a line. So that's where we see these patterns from. Let's see. We typically do this experiment at anywhere from 5 keV beam energy all the way up to 30. We can do it at just about any voltage you'd like, with the caveat that you have to be able to excite the phosphor screen and depending on what resolution you'd like to get to. So in the microscope, this is what it looks like. And I always tell people there's two kinds of people in this world, those who've hit something inside their microscope with this setup and those who haven't, or those who will. Here's our pole piece for our SEM, so our electron beam comes out of here. It strikes our sample, which is sitting here, and over here is our fluorescent screen. So our diffraction patterns appear over here. We then have a camera mechanism to image those. Down here we have some four-scattered diodes that pick up the four-scattered beam. Those are sensitive to the contrast we see in those is sensitive to the crystallography of the sample. So we begin to see the crystallography, channeling contrast, all sorts of interesting details on those detectors. You can see there's not a lot of room in here. Whoops, there's that button. But it actually, with a modern system, you can run this without hitting things too often. And you can use metallographically polished sections. This is a large piece of tantalum. This is a diameter here is about 1.5 inches on that sample. So we can put rather large samples in. And that's limited by the microscope. So why do we have to tilt? It's a pain, it's difficult, but really is important. So if we look at the number of backscattered electrons versus their energy, so we start with a 20 keV beam, and we look at normal incidence, we see that our backscattered electrons that come back out of the sample have this sort of an energy distribution. Not very peaked in any direction. And remember, when we're doing diffraction experiments, you'd like a monochromatic beam of whatever, X-rays or electrons. And so it turns out when we tilt to very high angles, like 70 degrees, those electrons go into the sample, come back out without losing very much energy. And those are the ones that form our diffraction pattern. So that's why we can use this technique to do diffraction, because we now have almost a monochromatic source of electrons that we use to illuminate our sample and form our patterns. In terms of resolution, what's happening? Well, if we think about, here's our beam impact point. Remember, we don't care about all the electrons. We just want to know where the ones that have lost very little energy come from in our sample, and that's very near our beam impact point. And so if you look here, here's the impact point. The green curve is for the electrons that have only lost about 200 eV, and we can see our resolution now is sub, tens of nanometers. Okay, so our spread here in this is sub tens of nanometers. Now the only difficulty is because we're tilted to some high angle, we do get that parallax down the tilt axis. So our resolution down the tilt axis is worse than across the tilt axis. But again, we can approach, in normal mode, 50 nanometer resolution is not that difficult on a modern system. And with other techniques, TKD, we can go down to 2 nanometers or so. I'll show you some examples later. Yeah. Great point. And yeah, you're right. But the thing that we care about are the electrons that come out of the sample that have only lost a few 100 eV of the initial beam energy. And then you ask yourself, where do they come from? And they come from an area very close to the beam impact point, okay? Because they don't have a chance to go very far and lose energy. And those are the ones that form our diffraction patterns. Now, the guys that lose more energy than that, all these guys out here, if we look at higher 200 kV or 2 kV losses, they contribute to the background of the pattern and the overall background level, we call that. So those they do diffract, but they don't diffract into these nice bands that we see. So that's why we can get resolution much better than you're used to seeing in normal backscatter images. Okay, so what about the beam voltage? We can do this, like I said, over a number of different beam voltages. I think this was from hematite. Again, purchased at my local rock shop. You can see the nice threefold axis up here. In the hematite, this is 5 kV, 10, 20, 30, and 40 kV patterns. What you notice here is that the only thing that changes, and you can convince yourself of this, is the width of these bands. The position of the zone axes don't change. Okay, so that gives us this nice stable way to measure the orientation. And the same thing happens with tilt. Does anybody do TEM diffraction or has had any experience? A few. So when you tilt in the TEM, you have the railrods, right? And so you can tilt 5 degrees and your diffraction pattern doesn't change a whole lot, depending on how you do it. Here, as we move that sample even 1 degree, we can sense that change in orientation because the pattern is rigidly fixed to our sample. And so it's very sensitive to orientation. So how do we actually do this? Commercial systems now do this quite well. I built my first system in 1992. It wasn't very fast at all, but it worked. So now we can buy a system that we scan the sample pixel by pixel, and you can pick the spacing of your pixels, how far apart they are. It depends on the microstructure you're trying to measure. We collect a diffraction pattern at every point. The system automatically finds where those lines are and the intersection of those lines, and then it compares that to a list of possible phase matches that we have listed. We index the pattern. We then, if we're plotting out orientation maps, everybody likes pretty color pictures. They end up on covers of journals, and they do make some nice, pretty pictures, I'll show you. But we can then plot the orientation based on this color scheme. This is a high entropy FCC alloy. This is a laser weld in that alloy right there. You can see that. And we plot. So a blue grain would have the 111 axis. And I think this was a normal image, so that would have the 111 coming out of the screen at you. and the red would have a 100 coming out of the screen. So we colorize our images that way. And we can do this now up to 3,000 patterns a second. And that's really remarkable. It's video rate crystallography in your SEM. Just the need for speed has been important, right? When I started, we were lucky to do 1 pattern a second. When we got to 10, we said, oh, it can't get any faster. We got to 100, and we said, oh my God, this is really wonderful. And just recently, within the last year, we're now over 3,000 patterns a second with commercial technology. So it's really neat to see some of these mappings. So this is a plot of the resolution of various micro beam techniques. We have micro Lowy here, we have COSL, we have EBSD, which is electron backscatter pattern. It's kind of an old slide. Here we have selected area channeling patterns, and this is the year. So I don't even know what this is, and that's number per second, 0.00. That's a lot of seconds to get an image. You can see EBSDs in the resolutions over here, so we're really pushing the resolution down and the speed up with year. And I stole this out of one of Austin Day's papers. It was a very good paper, by the way. I went back and I just sort of looked through the literature to see what people were saying in their papers. So this is, again, patterns per second over here, and this is the year. So back in 1990, 1995, we were still on that 1 or 2 patterns per second. And then suddenly, nobody talked about this for a while, and then in 2005, we got to 10, and now we're over 3,000 patterns per second. And the reason that's important is look at this scale here. So this is the time required to collect a 1 centimeter squared image with a step size of 4 microns, not including the stage moves, because that takes a second per stage move roughly. But if you look here, back in the old days, that would be 1,700 hours, totally undoable. But now when we're up around 3,000 patterns, you're talking a couple hours to cover a centimeter squared. So that's really a remarkable improvement. And as we get faster, I think we're going to be up where this sort of thing takes no time at all to get done. And so now we can do bigger areas. We can get the real picture of what the microstructure looks like. It becomes very important for us in the metallurgical community when we look at large grain materials like additive manufactured materials, which have very large grain sizes. I'm sure in geology there's many materials that have quite large grain size. I mean, I have some of those sitting on my desk, the nice euhedral crystals. And so being able to do bigger areas, I think, is really important and a nice improvement. This is some real data from a system in my lab. So this is, again, patterns processed per second. There's a lot on here versus how we set it up in terms of frames per second. This is a piece of tantalum. You can see here, depending on how we subtract the background or deal with it, we can get up to over 3,000 patterns a second. We can still index almost 100% of the pixels, right? So we're not losing much. Here's an example of some of the patterns. So here's the slow pattern at 5 milliseconds. I love to say that slow pattern at 5 milliseconds. We used to take seconds to get this. And down here, the fast one at 0.3 milliseconds. You can see that the pattern's still there. These computer algorithms are quite capable of extracting all the important features from that. And to show you that, this is a piece of tantalum single crystal, a nice single crystal of tantalum. If we look at the spread in all the patterns we collected for these maps, this is with the 5 millisecond dwell time, so that pattern. This is with the 0.25, so it's something like that. The total misorientation spread over those images are quite small. So this is 0.6 degrees in misorientation maximum. And you can see the slower is a little bit better, but not substantially different. So going fast is really good mapping. We can really get good data that way. So before I step into applications, is that kind of clear? Everybody get an idea of what we're talking about here now? It's both. So they've gone from the first cameras were film. I built my first camera with a piece of film in it. And that's, of course, less than a pattern per day, if you include developing the film and everything. Then the next we went to CCDs, which are fast, but not as fast as you'd like. And the new cameras are all CMOS based. And so they're very quick for readout, and they're very sensitive. There have been improvements in the phosphor screens, certainly. Typically, when we're running at 0.3 milliseconds or faster, we're using as much beam current as we can generate, maybe 10 nanoamps. with reasonable resolution still. So yeah, so there's a lot of beam current used, but generally we were always using as much beam current as we could get and dealing with the slower speeds. So now with the same beam current, with the increase in the efficiencies, the computer algorithms are faster, so they're really running really fast now. Yes, sir.
You're characterizing the tin whiskers. You have to know the orientation with respect to before you put it in the...
Yeah, that's the trick there. You have to just measure the angle using a parallax measurement, 2 tilt angles, 0, well, not 0, but 2 tilt angles, and you can get the, from parallax, you can get the angle of the whisker with respect to the surface, and then you just measure the orientation of that whisker, and you can transform that orientation to the whisker growth axis. It's easy for me to do. It takes a technologist about a day to do 40 whiskers. And every time I walk in with those samples, they were like running for coffee and trying to leave. But yeah, but you can do it. You just have to know, measure the angles. Right. And that's the trick. Without anything out of plane, you're going to have to know what angle you're dealing with. But with flat surfaces, it really doesn't matter. Okay. Yes, sir.
So, sort of maybe implicit, you didn't say this explicitly, but is there any...
Yes. So we can, well, it depends on what you mean by unknown. If
Or you have to be able to simulate the Kikuchi band.
actually what we can do is, going back to that earlier image where I showed you the nice rings, you can sort of see one there. They give us the spacing out of plane to within less than 1%, probably like more like 0.5% accuracy. So now you can develop a reduced unit cell if you've done XRD. We can use the same algorithms they use for reduced unit cells there. We can calculate a reduced unit cell, and we know that every crystal structure has a unique reduced unit cell, right? The what do they call it? The yeah, or there's another one. Oh, I forget the name for it. Anyway, one atom position, right? Per unit. So we know the one for BCC is a trigonal cell with 109 degrees between the axes. FCC is 60 degrees for the same cell between the axes. So every crystal structure has that reduced unit cell. We can begin to understand those and actually calculate what that cell would look like, and then come up to the matrix, what do they call it, the metric cell. Then you need some database to tell you what it is, but we have a lot of information. Correct. Yeah. You can get the lattice parameters and things like that. And you know the elemental analysis as well, right? So you're pretty far down the road to identifying an unknown. Now, I wouldn't use this for first principles. You know, if you're doing unknown of small crystals, you're probably better off doing XRD or micro XRD or whatever, micro Lowy, to get started there. But we can certainly go to a reduced unit cell pretty quickly. Okay, let's talk about meteorites. I got through Lehigh. I don't know if anybody knows who Professor Goldstein was there at Lehigh. He did meteorites for his entire career because he liked the iron-nickel system. It's a very commercially important system. But he studied meteorites because of the slow and cooling rate. And what they try to do with these meteorites is understand the cooling history of the body so you can understand the origins of these things. And if you've looked at any of the iron meteorites, they're this beautiful, a lot of them are this beautiful Widmanstätten pattern, where you have these plates of camosite surrounded by some two-phase regions of camosite and taenite called plessite. So we have these various structures in the meteorites. And so these guys go off and they measure the profiles, elemental profiles across these meteorites, and they come up with cooling rates. 1 degree C per million years might be a fast one. And they understand something about the origin of the meteorite. And there's been this discussion in the literature. If you start at high temperature, this planetary mass, or whatever you want to call it, floating around in space, is at high temperature. It's all going to be single phase gamma, the FCC phase, or taenite. And as it cools, it's going to transform to an alpha-2 martensite, which is really just ferrite or taenite. Sorry, camosite. I always get those backwards. And then the conventional wisdom was this martensite breaks down to the ferrite and the austenite again. Or here's the single phase microstructure, gamma, FCC, can go to martensite, but with a retained austenite phase. Okay, and then some of that eventually breaks down. The martensite turns to alpha, your ferrite, and you retain the austenite down to room temperature. And so the question is, can we determine the correct mechanism? It makes a difference on your cooling rate calculations. So Joe knew I was working in this area, and he bothered me with this problem. And I thought, oh, okay, we'll look at it for him. So here's the iron-nickel phase diagram. This is the nickel content and weight percent. Here's the temperature. So these meteorites I'm going to show you initially are about 18 weight percent nickel. You can imagine as it cools, the FCC phase follows this line. The BCC phase follows this line composition. And at some point, we get down here to the martensite start temperature, and we get this two-phase mixture. Now, phase diagrams are great, but they don't tell us what's really happening in the kinetics of these things. And what's really lovely about the meteorites is they're very slow cooling, so it's as close as you're going to get to what I would consider an equilibrium structure in this sort of a system. If we start to look at these, this is a meteorite called Toluca Valley. I guess they named the meteorites after where they found them. There was one out there that Joe bought me, and it was called Vaca Muerta, which I think means dead cow in Spanish. So you wonder if some poor farmer came out and found his cow dead on the ground with a big hunk of iron next to it. Anyway, so this is Toluca Valley. Here's an image. This is an EBSD image. So what we do to form this image, we actually plot at each pixel some measure of how clear the diffraction pattern was, and we get these beautiful microstructural images. Here's the inverse pole figure with respect to the x direction, although in this it doesn't really matter. But the thing you should notice, well, I should also say this is the phase map. So the red is the taenite, or the FCC, and the blue is the camosite, or the BCC phase. If you go back to this now and you look at everywhere there's taenite, you see that it's this green color everywhere throughout this meteorite. So all that austenite is the same orientation. And as a metallurgist, I look at it and go, oh, that's retained austenite. We see this all the time in quenched steels, right? It's something that happens because as you cool, you reject nickel from the camosite, it enriches the taenite and pushes that transformation temperature very low. So it never transforms to the ferrite phase. Well, in the meteorite community, oh, and then this is just further proof of this. If you look at this, here's the map or the pole figure, the 111 pole figure for taenite, and you can see it's mostly single orientation. Some of the speckling is due to some minor misindexing in the patterns or some exsolution or precipitation, as we metallurgists call it, of further austenite from the alpha phase. And over here's the pattern from camosite. Very striking pattern. And obviously, if you see a single crystal ferrite or austenite like this, and you get this pattern from the camosite, you can tell there's a relationship between the austenite and the ferrite phase that forms. And I'll show you that in the next slide. So if we think about this, so here's our taenite, here's our camosite. We think about these orientation relationships. One's Nishiyama-Wasserman, the other one's Kirchhoff-Sachs. Basically, close packed planes are parallel to close packed directions. If you start with an austenite of this orientation, and you allow all those variants to form from those close packed directions and close packed planes, you end up with a pole figure that looks like this. Very similar to what we've already seen. So that's not the big surprise. What's interesting, if you start looking throughout the meteorites, and we only looked at the 4 Bs for this initial study. This is Chinga, Toluca Valley, Weaver Mountain, Hoba, and we looked at a number of other ones. And in every case, if you look at the austenite, which is always ringed around the Widmanstatten plates, it's always the same orientation. So this is now showing us that we have a more applicable mechanism throughout the meteorites formation. Again, if we look at all those pole figures, we see the same thing, that it's some mixture of this KS and NW. Here they are over here. And it's well known in the literature that when austenite turns to ferrite or ferrite turns to austenite, we see these orientation relationships. And so what this leads us to is the conclusion that the current wisdom was wrong. Okay, so now imagine out in space, you have this big meteorite floating around, it's a high temperature, it's got these huge grain sizes in the prior austenite, right? So grain size maybe 50 meters. something like that. We hardly ever see grain boundaries or evidence of a grain boundary in a meteorite fall. I've yet to see one. I think the ones that are out there that actually do have grain boundaries, I've seen pictures, are thousands of dollars to purchase or to get your hands on. So anyway, so we start with this great big austenite. As it cools, it reaches that transformation temperature, the martensite forms, and we retain the original orientation from that parent body of the austenite phase, or the taenite. And then on subsequent cooling, the martensite becomes ferrite, just because we get rid of a little extra tetragonality, and we retain the original gamma. And of course, this changes the way they modeled the cooling rates in these meteorites. And you know, if you make nice color pictures, they end up on covers of journals. Management loves that. So they make a big deal out of every time you get a cover. So here's the Meteorites and Planetary Sciences. We did this work back in 2006. So I thought that was a really nice application. Now, since then, I've started to play around with some bigger areas now that we can do it. You notice those areas were maybe 100 microns in size. So this is Gibeon. This is a slice of Gibeon. It's pretty easy to come by. I mean, there's 26 tons of it laying around. You can purchase this, or you can maybe borrow it from somebody. But I thought it'd be interesting to look at bigger areas now to see if that theory holds. And certainly here's a large area. This is 21 millimeters by 9 millimeters in size, so that's a rather large section. This is about 2,100 individual fields stitched together, 2 micron step size. This took about 9 hours, so that's overnight, not a big deal. A full 40 minutes of that is actually just waiting for the stage to move from each one of those positions. Okay, and we can actually go in, so this area here, if you look at it, is this area. And again, we're seeing that same thing. All the green is the austenite. And you see it maybe better over here where we've colored just the austenite and then put the microstructure behind it. And as we look around this meteorite, we see the same thing. So many, many millimeters apart. This is the two maps, or the two pole figures from that large area of Gibeon. Again, you can see this obvious single orientation of austenite, and then we get the same pole figure for the kamacite phase. And you can see we have that NW-KS orientation relationship. And then we can look at other ones. This is Toluca. This is an older slice that I have laying around. This is a millimeter bar. So you can see this huge Widmanstatin pattern here. These plates are quite massive. We can do some really interesting things with this one, because this isn't just austenite and ferrite. This one has cohenite, which we call cementite in metallurgy, or iron carbide. It's also got schreibersite, which is a phosphide. And so the red is the ferrite, kamacite. The blue is the austenite. The green is the carbide. And the yellow, you can see it around here, is the phosphide. So from an EBSD map, we can understand all that. If we cared about the carbide relationships, we can get all those done. But again, if we just look at the orientation maps, and this turns out to be a rather large area as well. This is a centimeter. Here's the orientation map. Again, we color it with respect to these sorts of color keys. So there's schreibersite. This is the FCC or the BCC phases. And there's the cohenite. Uh-oh, I broke it now. Oh, there it goes. And so we can see a rather large area of that sample. And again, if we plot up our pole figures, we see the FCC is all of one orientation, and our BCC has the same sort of NWKS relationship with the austenite. So this is more ubiquitous across the meteorites than we thought originally. So again, I think the impact here is that the way we think about cooling rates and the modeling in these meteorites has changed now because of this work. So just to give you something I'm a little more interested in my field, right? Does Sandia really care about meteorites? No. But you know, it's a great way to learn these orientation relationships because it is more of an equilibrium study. We do a lot of inertial welding in our lab, and inertial welding is simply take a rotating part, spin it up on a big flywheel, slam it into a stationary part, and let inertia slow it down to a stop. You get a liquidless bond between the two parts. So it's quite nice, and no melting's involved, so we have none of those problems. You get great dimensional control. And what happens, what we're interested in is the microstructural development. Just so happens we do this in stainless steels, where we start with an austenite, and we do see ferrite formation. So that's one of the reasons I started looking at meteorites, so I could really understand them. So here's one of those welds. Here's the inertial weld interface. You can see the fine-grained regions here. This is in a 21 chrome, 6 nickel, 9 manganese. It turns out to be an austenitic alloy. We slam those two together. We get this nice zone of this nice weld zone. When we look at that with EBSD, and what I've done here is just color the body-centered cubic phase, the ferrite, and you see now in that weld we're generating a lot of body-centered cubic material. And this application, the body-centered cubic, is not, it's not a good thing to have. So again, these common orientation relationships, I mentioned these earlier. We won't see, well, I should just move on. So here's the issue, that when you have this bond and you have a hydrogen environment, the hydrogen tends to travel along and crack. This is a crack. Travel along and try to find the body-centered cubic or the ferrite phases. So this is bad in our application. And we'd love to eliminate it. So if we just do EBSD of that real quick, you can see that this colored region now are the ferrite regions, and the background is the austenite. And if you look carefully, you can see those regions where the ferrite all has the same orientation, like there. Here's some all same orientation. So these are really indications of the prior ferrite grain size when we heated this up. Okay, so now we're getting an idea. And if we actually look at that, I don't know if you can see it from back there, but there's little red and blue lines on here. Those are the interfaces that have the Kirchhoff-Sachs or Nishiyama-Wasserman orientation with the surrounding material. And so we're again seeing the inverse of the meteorite. We started with a body-centered cubic phase, and now we've transited. If we go back to the phase diagram, by knowing the size of those regions, we can actually know the starting microstructure at high temperature. So again, it's the same idea with the meteorites. We're trying to figure out the cooling rate and how these structures formed, and maybe understand how we can get rid of them. And so that's my pitch for why I studied meteorites, because we were studying these sorts of alloys at the same time. In the last 5 minutes of the talk, I'd like to just show you some of the high resolution EBSD we can do. And so this is called TKD, transmission Kikuchi diffraction. So we make a thin sample. And we can do it in 2 different modes. So we put our little thin sample here on the end of this holder. There's our pole piece. Here's our EDS detector. So we can do both elemental mapping and crystallographic mapping at the same time. Here's our conventional geometry, where the phosphor is vertical. There's other geometries out here where we can put the same sample, pole piece, but we put the detector underneath the sample. It's sort of an on-axis geometry. So here's the conventional pattern, TKD. Here's the on-axis. We have this very bright spot in the middle because that's the transmitted beam. But we get enough of the Kikuchi pattern that we can index it. And we can go down to certainly extremely low resolutions. Here's an example from a wear scar. So we have a lot of work at Sandia in contacts, switches, all that sort of thing, because we'd like to know how long they're going to last and whether they're going to be reliable. So we do a lot of measurements. So here's our thin sample. This is the wear scar. You can see the fine-grained region. This is a fib-prepared sample. And over here we have our TKD maps. This was at 10 nanometer step size. We get some very nice work. This is at 3 nanometer. And now you get an idea that you can actually see within a few nanometers the grain size. You resolve a lot of the information within here that we couldn't get with normal bulk samples because of the size of the interaction volume and the size of the electron beam. So we're really starting to push this to very, very, very low or high resolutions, if you will. Of course, the problem here is if you're trying to do 1 micron at a couple nanometer spacing, that's a lot of pixels. So these tended to take a long time. SEMs aren't set up well with stages for long-term drift problems. So we were starting to see the fact that drift was becoming very difficult to deal with. However, these new fast detectors now have fixed that for us, because a typical map now, the map I just showed you, this is at 10 nanometer steps, took about 3 minutes to collect, right? So we don't have to worry about drift so much anymore, long-term drift. Back when I was doing this for the first time. These were thicker samples, but this was taking an hour or so to collect even at 25 nanometer step sizes. And so these new fast detectors really make this transmission mode very useful, and we can push the resolution certainly way down to a few nanometers. And I think it's a really nice development. I would argue that this is better than anything that TEM can ever offer us. I know those are fighting words, I'm sorry. Except for the newest precession diffraction, the nanomegas, that sort of thing. We've had long technical discussions about what they measure versus what we measure with EBSD. And the two are quite different, and you see differences in the patterns, or differences in the maps that you get. But certainly being able to do this all in one tool is really nice. And so I'll conclude. I hope I've convinced you that EBSD is an important, invaluable tool for characterization of crystalline materials. It's now to the point where it's fast. We don't have to waste hours and hours of machine time collecting these beautiful maps. Of course, we can do it at high speed, like I said. Again, now there's little trade-off between the speed and the accuracy of our measurements, provided you have a great sample. Large area EBSD maps, I think, are critical to our understanding of macro scale properties of materials. And I find that now that we can do that, that's what everybody wants. Before they were dissatisfied with 100 micron sort of maps. Now they want to see millimeter or bigger. And again, that brings up this whole big data problem, right? So now we're talking about many, many gigabytes for a map. I think some of those big maps from the meteorites were on the order of half a terabyte when you get done. So it's a lot of data. We really need the computers to catch up. TKD, absolutely wonderful. We can do great stuff with it. And again, now we can characterize thin samples at very high resolution. So I think I'll stop there, and thank you for your attention.
Any questions for Joe?
Just a practical one. When you're looking at your at thin samples, how thin do you have to be? Because with the 30 kV electrons, especially if you're doing it in sort of transmission, you need to have fairly thin samples.
Yeah, we try to make them about 100 nanometers or so. So it's a typical fib sample, nothing beyond that. In higher atomic numbers, sometimes we'll actually use the fib to actually mill till we get a perforation in the sample. And then around that, just like in electropolished samples, is a thin area we can deal with. It really depends on the material. So if you're dealing with silicon, it's easy. If you're tantalum, it's a little bit more work. It has to be a little bit thinner. But we find that we can find a suitable range of sample thicknesses for most materials with a fib. That's mostly what I've done is fib sample prep. Somebody else had a question?
So at the beginning of your talk, you said if you're studying crystalline materials, you're missing out if you're not using this technique. But could you comment on the state of the art for electron beam techniques for non-crystalline materials or paracrystalline materials, if there's any chance?
Oh, let's see. We have tried to look at things that are either extremely fine-grained, nanometer sized, and we run into some problems there with the resolution. Again, the sample has to be extremely thin at that point, so that's tend to be a problem. If we start to get into the things that aren't crystalline, you might see some, you might be able to do nearest neighbor sort of things, although it's difficult in that area, hasn't been studied a lot. Some of the crystalline polymers, there's been some recent work in the crystalline polymer area, and they've gotten some wonderful patterns and been able to do some of the mapping that we've been talking about here. There was recently a published paper in Microscopy Microanalysis where they looked at polymers and got some beautiful patterns from these more crystalline polymers. So there's things you can do there. I think the major problem I see with a lot of those sorts of materials is that we are using a 30 kV beam. We're using a lot of beam current, and so beam damage is going to be something you're going to have to deal with. So whether you do that through cooling or some other mechanism, it's something you're going to have to think about. Anybody else?
So I noticed that now the resolution is about 10 nanometers. So can you resolve the crystal defect in your technique? For example, individual dislocation. You can see, I'm pretty sure you can see the submarine boundary, but how about the individual dislocations?
There's been some recent work, look up the papers by Angus Wilkinson and Ben Britton, where they're starting to push the technique, the strain analysis technique, to that point where you're starting to look at single dislocations and look at the distortions around a dislocation in metals. Where the core might be rather large compared to maybe in a ceramic or something like that. But in metals, they're certainly starting to push the science that way and doing strain analysis around dislocation cores. So there is some work in that area. It's new, past 2 years or so. So it's just brand new stuff. But they do a cross correlation, so they actually need a pattern from undistorted material. And then they do cross correlation all around for every pattern they collect. And they can do subpixel shifts and subpixel strains and actually calculate the elastic strains around features in a microstructure. Yes, sir.
Thanks for a great talk, though. It's a totally off-the-wall question, but I'll ask it anyway. Is there any hope to do something like electron backscattering detection off of, say, photo-emitted electrons? So using an X-ray source, tunable X-ray source, and you're going to generate, I don't know if
They're very low energy, right?
Yeah.
Photoelectrons. So the problem there is, well, you could end up in like a lead or a sort of pattern. We do see spot patterns quite often in some of our EBSD patterns. So the question of how low can you go and how do you detect those might be the hard part, right? Because we do lead, people do lead and they have these nice channel plates and things. We have not even gone anywhere near that yet. But in principle, it seems to me that you could probably do something depending on how close you can focus your X-ray beam. Yeah, sure.
Any other questions? All right. Well, please join us for lunch right now. And Joel will be around for the rest of today and tomorrow as well, tomorrow morning. Let's thank him one more time.
Thank you.